Hello and welcome back to another stats warm-up. So let's take a look at what we have here. The elderly fear crime more than younger people, even though they are less likely to be victims of crime. One study recruited separate random samples of 56 women and 56 women and 63 men over the age of 65 from Atlantic City. Of the women, 27 said they felt vulnerable. 46 of the men said this. Construct a 90% confidence interval for the difference in population proportions. And specifically, we're going to do men minus women. Does your interval give convincing evidence of a significant difference between the population proportions? All right. So we're going to use the 2 proportion because we've got data on men and women, Z interval. All right, so if we go to our menu here, stat tests to proportion Z interval, it wants to know X1, N1, X2, N2, and our confidence level. All right, confidence level tells us that the problem tells us that we're using a confidence level of 90%. And then as far as the other stuff goes, because it says men minus women, we're going to put the men first, and we're going to put the women second into our calculator. All right, so that it does the subtraction in the correct order. All right, so we had 63 men and 46 felt they were vulnerable to crime. We had 56 women and 27 of them said they felt vulnerable to crime. All right. So once we put all of that in there, 46, 63, 27, 56, confidence level of 90%. All right. It will give us an interval of 0.10475 to 0.39128. Now remember, this is an interval for men minus women. So we are 90% confident the true difference men minus women is between 10.5% and 39.1%. All right, so this is indicating that men feel they are more vulnerable to crime 10 to almost 40% more than women feel that way. All right. So according to the data that we gathered, men feel far more vulnerable to crime, or at least older men do, than older women. All right. Does your interval give convincing evidence of a significant difference? Yes, the difference is significant. Because our interval does not contain 0. Remember, 0 would be no difference. So when we don't contain 0, that's saying that we think there is a significant difference. Now, we did a 90% confidence interval, so technically this only matches up with an alpha of 10% instead of the usual 5%. But in this case, even if we had switched it to 95% confident, we were still going to end up saying that the difference was significant. All right, a study of the National Athletic Trainers Association surveyed random samples of 1,679 high school freshmen and 1,366 high school seniors in Illinois. Results showed that 34 of the freshmen and 24 of the seniors had used anabolic steroids. Is there a significant difference between the population proportions? State your hypothesis and conduct the appropriate test. All right, so our nulls for these are almost always the same. It's just that the proportion of freshmen equals the proportion for seniors. The other way you can write this is that PF minus PS equals 0. You don't have to write it both ways, but either one of those is fine. And then the alternative, in this case, it just says, is there a difference? It doesn't say, is one higher than the other? It just says, is there a significant difference? So we would just say that PF does not equal PS. Or again, you could write that PF minus PS does not equal 0. All right. But all it's asking for is a significant difference, which is what's telling us that we should be using not equal to in this scenario. Then again, we'll use our alpha of 0.05. And this time, instead of using a 2-prop z interval, we're going to use the 2-prop z test. All right. So we go to our calculator, we go to stat tests, 2-prop z test. It's going to ask for x1, n1, x2, n2. And then this time we are doing that P1 does not equal P2. All right, so our P1 was 34 out of 1,679. And our P2 was 24 out of 1,366. All right, so let's get that in there. 34, 1,679, 24, 1,366. We're doing a not equal to. All right, hit calculate there. So there's our two percentages. We're basically saying 2% if of the freshmen, 1.76% of the seniors. Is that gap significant? Is the gap between those two sample statistics significant? Is it large enough that we can think there's a real difference? And, sometimes you might say, oh, that's really small. There's no way that's significant. But you have to remember we had really large samples. So that's why we go through this procedure, just to make sure. So we're getting a test statistic of 0.5382. Which is giving us a p-value of 0.5904. So your instincts, at least in this case, were probably correct, that no, that gap's pretty small. It's not significant. So in this case, because our p-value is over 5%, we fail to reject the null. And then 3 says, construct a 95% confidence interval, and then are the results consistent of the hypothesis test? So if they are consistent, we're expecting an interval that contains 0 because we failed to reject the null. All right, so that's what we're expecting. Let's see what we actually get. So we're going to do a 2-prop z interval, x1, n1, x2, n2. Confidence level is going to be 95%. And then these are all the same as what we just did. 1366, 24, 1679, 34. All right. When we put that in there, 2-prop z interval. All right. The numbers are already in there for us. I just have to change the confidence level to 95%. All right. We are getting an interval from negative 0.007 to 0.01237. All right. So this is saying We are 95% confident. The true difference, and for this one, I did the freshman first, so freshman minus senior, is between negative 0.007. So we could also write that as, why don't we write that as a percentage? Negative 0.7% and 1.24%. Go with. All right, so notice that this interval contains 0, which means we're saying it's possible that there's no difference between these two. All right, because the only way you end up with a difference of 0 is if these two are equal, which is saying, no, there's no difference. And we can't rule out that possibility because 0 is inside of our interval. So they are consistent. The results are consistent, which is what this is showing us right here. Okay. Take a look at the back. Aspirin prevents blood from clotting and so helps prevent strokes. The second European stroke prevention study tested whether adding another anti-clotting drug named dipritamol would be more effective for patients who already had a stroke. Here are the data on strokes and deaths during the 2 years of the study. All right, is there a significant difference in the proportions of strokes between these two treatments? Now, I will fully admit that this problem is a little ambiguous, and there's probably two different ways you could set it up. And I would be sympathetic to either one of those structures if it was like a quiz or a test. So some people might focus on this and say, is there a significant difference? And say, oh, okay, that's a not equal to situation. Some people might focus in on this and say, oh, this is a, greater than or a less than situation. So some people might look at this and say, oh, we're doing a one-tailed. Some people might focus in on this and say that we're doing a two-tailed. I would be sympathetic to either argument on a problem like this. So as long as you're doing it correctly, I'm comfortable with that, given the way this problem is worded. I'm going to do it as a one-tailed test, which kind of makes sense. You're adding this new drug and you're hoping to find an improvement. All right. So again, my null hypothesis is I'm just going to write this as that the proportion with aspirin is the same as the proportion with aspirin plus. All right. So A plus D. All right. Now, the alternative, and again, you have to be careful because you have to make sure you're interpreting these correctly, but we're looking at the number of strokes. We're looking at the percentage of strokes here. So for me, I'm saying, oh, I hope that PA is greater than proportion of A plus D, right? Because effective for us means less strokes, which means a lower proportion. All right, so based on how I've set this up, I'm expecting an alternative where A is greater than A plus D. And again, greater than in this case means more strokes, which is a bad thing, obviously. All right, so I'm going to use my alpha of 0.05. And then we're going to do our 2 prop Z test. All right, my X1 is going to be the 206 strokes. My N1 is going to be the 1649 patients. My X2 is going to be the 157 strokes. My N2 is going to be the 1650 patients. And then again, let's bring this up on the calculator first. All right, so 2 prop Z test, 206, 1649, 157, 1650. I'm expecting that P1 is going to be greater than P2. I'm expecting that the number or the percent of strokes with aspirin is going to be greater than the percentage of strokes with aspirin plus dipridamole. Probably not saying that right, but either way. All right, so when I run this, I get a test statistic of 2.73. I get a p-value of 0.006. And again, that P1 hat, P2 hat is just showing you your proportion. So basically, aspirin alone had 12.5% strokes. Aspirin plus the drug had 9.5% strokes. So we saw a 3% decrease. Is the 3% decrease significant? That's what we're asking. Is a 3% drop significant? All right. And based on our p-value, it is. All right. So because our p-value is under 5%, we reject the null and accept the alternative. So in this case, we're saying there's convincing evidence that the drug does help. All right, describe a type 1 error and a type 2 error in the setting, which is more likely to be serious. So again, a type 1 error is when you reject the null and you are wrong. So type 1 would be, we think the drug helps and it does not. Right? Type 2, in this case, would be the drug helps, but we don't realize it. All right. So, which one is more serious? Again, technically, we need to have a little more background information, but assuming the drug doesn't have side effects, type 2 would be worse. All right. Because then you might not give people the drug, even though it helps. All right. Type 1, we think the drug helps and it doesn't. We give it to the people. As long as it's not hurting them and it's not giving them side effects, then it's not a huge deal. So it's not a huge problem in that case. But a type 2 error where it does help and we aren't aware of it could be a much more unfortunate scenario there. All right. So last question. A researcher reports that 80% of high school graduates, but only 40% of high school dropouts would pass a basic literacy test. Assume that the researcher's claim is true. Suppose we give a basic literacy test to a random sample of 60 high school graduates and a separate random sample of 75 high school dropouts. Find the probability that the proportion of graduates who pass the test is at least 20% higher than the proportion of dropouts who pass the test. Start by finding the mean and standard deviation, then use normal CDF. So we're basically saying, AR, what are the odds that when we do percent high school minus percent dropout, we get an answer 20% or higher. So to do that, we have to create our sampling distribution. Right? To answer this question, we need our sampling distribution. Right? So the center of our sampling distribution, all right, or the mean of P1 minus P2 is just 0.8 minus 0.4 or 0.4. Right? The standard deviation of P1 minus P2 is where we have to use our big formula here, which is P1 Q1 over N1 plus P2 Q2 over N2. All right. So if we fill this in, we're left with the square root of 80% for high school graduates. So 80% times 20% divided by how many high school graduates did we talk to? 60 plus 40% times 60% over the 75 dropouts that we talked to. And then that just becomes, something that you're doing on the calculator. So I've got 0.8 times 0.2 divided by 60 plus 0.4 times 0.6 divided by 75. I can take the square root of that, and I get a standard deviation of 0.766, we'll say. 0.766. So these two numbers are used to generate a curve that's centered at 0.4. And we're basically saying, what are the odds of getting 20% or higher? All right. What are the odds of getting a gap of 20% or higher from this curve that these two numbers just generated for us? So we're going to do an NCDF from 0.2 to 9999 for a curve that's centered at 0.4 with a standard deviation of 0.766. All right. And let's see, 0.2 to 9999 when we're centered at 0.4, and our standard deviation is 0.766. All right. Gives us a result of basically 99%, 0.9955 or 99.5%. So a really high probability, which makes sense. If we expect the gap to be 40%, all right, the odds of getting a 20% gap or higher is pretty likely because the expected gap is 40%. So if I'm going 20% below what we expect, I'm getting pretty much the entire curve, which is what we're seeing represented there with that result of 99.5%. All right. So I hope this was helpful. Obviously, if you have any questions, just let me know. Otherwise, have a great day.